everybody, and welcome to Echo Live. My name is Anna, and of course, I'm coming to you from the Michigan Science Center's Echo Distance Learning Program. We have a really cool, exciting program planned for you today, another chemistry episode of Echo Live. And today we're going to do some really cool science experiments that I found online. You know, if you're like me and you really enjoy science, and maybe you're not getting enough science here on Echo Live, you might do one of my favorite things to do, which is just hop on Google, type in cool science experiments, and see what pops up. Now, when you do that, I found all sorts of really amazing, pretty fascinating science experiments, but not all of them explain the experiment. Not all of them do a good job of understanding the science that goes behind them, but I picked three really cool science experiments that I found online that I think do a good job of tying together a lot of the content that we've covered here on Echo Live. Now, we've talked about chemistry a lot. So if you haven't done so already, and you are in the process of introducing yourself in the chat feature of whichever program you are joining in on, whether that be YouTube, Facebook, or right here in Zoom, you can tell me in the chat too, what is chemistry? Based on what we've learned over the past couple months together, we've done a whole lot of chemistry, right? We know that we do experiments and reactions, but we've also talked about the definition of chemistry. Now, does anyone remember what that definition is? We work with a lot of really cool equipment. So while you are thinking about that definition of chemistry, what I'm going to do is suit up with some more personal protective equipment, or PPE. I'm sure we're all pretty used to wearing some PPE out in the world now, but PPE is especially important in a chemistry lab or anytime you are doing science, especially when things can be a little bit dangerous. And some of the activities I'm going to try today can be dangerous if you are not trained in taking safety precautions. So of course, we're always going to be safe. For that reason, I'm going to put on my safety goggles here to protect my eyes. I've got my handy dandy lab coat on, of course. I always wear my lab coat when we're working with harsh chemicals or open flames, which is why I also have my gloves. These are my fire gloves. These ones are to protect my hands from being burned by any sort of flame that might come near me. But of course, I also have my fire extinguisher as well. Now, I don't plan to use the fire extinguisher here on the show today. I've never had to use the fire extinguisher during an experiment on Echo Live, but we always have it here just in case. We're always prepared. We know how to use it. We make sure that it is current and up to date. And last disclaimer about safety is that you probably have a fire extinguisher in your own home. It's a really fantastic idea to have one because we've talked about fire a lot. We know that it's extremely dangerous, but it's also not that hard for a fire to start. There are all sorts of things that could start a fire accidentally, and having a fire extinguisher in your home is a great idea. If you have one, definitely check the dates on your fire extinguisher because they do expire. Just like your milk might expire, there's a shelf life on a fire extinguisher. So your homework after Echo Live today, your reward for all of these really cool experiments that we're going to try is you are going to practice good fire safety at home by, of course, never playing with fire, but by checking out your fire extinguisher at your house as well. Now, let's see. Did anyone tell me what they think chemistry is? I see some answers starting to pour in here in Zoom. It is definitely a cool science thing that we do. Some people are naming lots of different chemistry experiments that we've done together. These are good answers. Now, chemistry generally is the study of matter, right? So talking about those atoms and molecules that we find on our periodic table, the atoms on the periodic table, combining them together to different molecules, making and breaking bonds, right? That's all chemistry. Now we are going to start with a pretty interesting reaction that has to do with the fire triangle. Now, I know as much as you guys are experts on chemistry, you are especially experts on combustion, or the three pieces of the fire triangle that it takes in order to have a combustion reaction. I'm sure you can name them for me in the chat. Go ahead if you'd like to, but I'm also going to pull up a diagram here on screen just in case anyone has forgotten their fire triangle components. To have a combustion reaction, to have a fire and sustain a fire, we need fuel, heat, and oxygen. If we're missing any one of these three things, we no longer have a combustion reaction, or your fire might go out, which can be a good thing. Say, for example, when you are snuffing a flame. So if we know that we can suffocate flames by taking something like a dish and stopping any more oxygen from participating in our reaction. That's actually what I'm going to plan to do for some of my reactions today. So by removing a piece of our triangle, right, we can remove our fire, our element of fire. Now, today we're talking about kind of somewhat of a science myth. Now, we're going to try to talk about spontaneous combustion. And people talk about spontaneous combustion all the time. Maybe you've heard of it. There are all sorts of crazy stories out there about people or objects just randomly bursting into flames. Now, there's no scientific evidence of that kind of spontaneous combustion really happening in the real world because it's hard to take evidence or data on something that is spontaneous, right? So we don't have any proof that that kind of spontaneous combustion happens, that a random object for no apparent reason, without the addition or combination of our fuel, heat, and oxygen might just burst into flames. But if we're going to cover another dictionary definition, I know 2 in a row right here on Echo Live, when we're talking in chemistry about spontaneous combustion, we just mean a combustion reaction that happens at or below room temperature. So at a fairly cold temperature is what we're talking about. And we can actually accomplish that using just 2 ingredients, which you might also be thinking to yourself, just 2, right? We're actually going to seemingly be missing one piece of our fire triangle here. The 2 ingredients that we're going to combine are potassium permanganate and glycerin. But we're not going to add any sort of heat to this reaction. Now, we've talked about heat before, that it can come in many forms. I could take something like a lighter and ignite a combustion reaction, right? That could be a source of heat for a fire. I could also take something like a match, and even though I don't have an outside source of heat, I can turn my own mechanical energy, right? The energy of my hand moving, and I can actually light a match just like this, right? Mechanical energy, thermal energy, or heat, right? Those are all just evidence of kinetic energy, of motion. So we can use all sorts of stuff as our source of heat, but we won't be putting any heat into our reaction here. Now, what we're going to do is I'm going to put on my gloves here just so we're being extra safe, and we're going to just simply combine our potassium permanganate, which is a powder, and our glycerin, which is kind of a very viscous or thick liquid. Glycerin is usually found in things like bubble solution. It's what helps your bubbles kind of hold their shape, makes them a little bit thicker and more durable. And this potassium permanganate is the same stuff that we used last week when we did our radish experiment. So if you remember last week on Echo Live, we did an experiment where we took some potassium permanganate, we dissolved it in water, and put it in a slightly acidic solution, which gave us a pink solution. But by stirring in something acidic like a radish, this potassium permanganate acted as an oxidizer, which is exactly the goal of this experiment right here. Now I'm going to zoom in so everyone can get an up-close look at our first attempt at spontaneous combustion. All we need to do is just add our glycerin, this very thick, viscous liquid, just on top of our potassium permanganate, and then we just wait, right? We're not adding any heat. We're not adding anything else to our reaction. We're hoping that just by the combination of these 2 ingredients, we will have spontaneous combustion. Wow! And it looks like it worked, right? We said in a past episode of Echo Live that combustion reactions require 3 ingredients. They take fuel, heat, and oxygen, but they also produce 3 things. They produce heat, light, and smoke. Now, I think over the camera, you could observe at least 2 of those things. I'm hoping that you saw light and smoke. Let me know in the chat, did you observe light and smoke? And it's not quite safe, right? I don't want to check with my hands by touching it, but by just holding my hand near or kind of above our reaction, I can tell you that it got incredibly hot. So we certainly had a combustion reaction. All this did was take our two ingredients here, and this reaction is so exothermic. The oxidation, what happens to the glycerin when it is absorbed into the potassium permanganate, it is so exothermic that just that chemical process alone heated the reaction enough to the point of ignition, where we saw a very, very bright, very, very purple, hot flame. Now, potassium permanganate, you can obviously buy it from a chemistry lab because we're using it as a chemical for some of our reactions here, like we've been doing so far. But it's also sold as a medicine, which is pretty interesting. So this can be used to treat athlete's foot. It can be used for acne, but it's also used by hikers or mountaineers. So they carry a little bit of potassium permanganate with them when they are hiking through pretty rural or pretty obscure areas. In case they were to get lost, they're actually able to sprinkle this potassium permanganate into the snow or into the areas around them, which can create these really, really hot reactions without the use of something like fire. And so they can produce smoke signals, they can write messages on the ground using just one very simple ingredient that did not require them to carry a lighter or a fire starter or anything like that. Now, remember throughout our program, if you have any questions, you can definitely feel free to ask in the chat. I'd love to answer them. Like I said, I found these reactions online. So I found this one quite a bit. I hadn't found it really explained very well, but I thought it was pretty cool that we had used this potassium permanganate for a reaction last week, and we can use it for something totally different here on Echo Live. And now we understand how versatile some of these chemicals can be. Now, in our next experiment, we're going to be doing another combustion reaction. This one is called creating a sugar snake. The reason I want to show you this one is because oftentimes you find this one online listed as cool science experiments that you can try at home. But I will put that with a disclaimer. This next experiment, creating these sugar snakes, also uses a combustion reaction. Now, I would never recommend playing with fire at home. So instead, I thought we could just do it here on Echo Live, that we could do this experiment together, talk about the science. You guys could have some chances to ask questions. That way, in case you did decide this is something you wanted to try at home, although I don't recommend it, we'll at least have an understanding of why this might not be a great idea. For this, all you need is some really simple household materials, which is why I think people find this one or recommend this one online so often. The only things you'll need is sugar, baking soda, some sand, and some flammable liquid. So my flammable liquid that I chose is isopropyl alcohol. Some people recreate this online with lighter fluid, but I found that isopropyl alcohol really works the best out of any fuel. It burns at a relatively low temperature compared to some other fuel sources. And so this one works really great for this reaction. The reason we do this over sand is because the sand is going to contain our reaction here on the table. And so all we're going to do is create a couple puddles of fuel, 2 puddles, because I have 2 sugar mixtures that we're going to test out so we can make some observations together. It's one of our favorite things to do here on Echo Live. So I've got 1 fuel pile right there and 1 fuel pile over here, leaving some space in between them so that we have 2 separate sugar snake reactions going. And then let's talk about what we're using for sugar fuel. In this container, I have one that's labeled PS because this is powdered sugar mixed in with baking soda. And we're just going to take a little bit of it and form it into kind of a mound right on top of our alcohol fuel. Not too much. In our next reaction, let's see, I had a different spoon. We have just confection sugar, which is granulated sugar that you would probably find at, you'd probably do have this at home. Powdered sugar is a little less common. Maybe you have it. I don't usually have it in my home because I don't really use it for anything because I don't think it tastes like anything, which kind of defeats the point of being sugar, in my opinion. All right, so we've got 2 fuel piles here. And what we're going to do is just ignite the flammable liquid underneath them. And then I want us to make some observations about our 2 reactions as they go off simultaneously or at the same time. Make sure our camera focuses here. It wants to focus on my glove instead of our reaction. There we go. All right, so we're just going to take our lighter, or you could use a match, I suppose, and we're just going to ignite the fuel and make some observations about these two reactions. This one is not appearing to light. Our first one is getting started there. See, we never want to add fuel onto an open flame, so we're not going to do that. We're going to try to get our fuel source to light here. There it goes. Seems like it's going out relatively quickly. Try this again. Try our best to get that one ignited. If not, we'll probably just have to put out our other reaction and get started again, because you would never ever want to add fuel onto an open flame. I'm sure you can guess why, right? Because if I were to now open up that bottle of fuel, the flame could travel in through the stream of liquid back into my bottle and create a giant fire explosion inside that bottle. It's totally unsafe, so we are not going to do that. But we are starting to get some really good results from our two combustion reactions here. Now, what's interesting is one thing that you can't observe over the camera is the way these reactions smell. And they actually smell really delicious. It kind of smells like toasted marshmallows because we're actually going through a very similar process. When that combination of sugar and baking soda burn, they actually produce carbon dioxide gas. If everyone at home takes a deep breath in and out, carbon dioxide makes up a good chunk of the air that we exhale or breathe out after we use the oxygen from the air around us. Now, as this carbon dioxide is being created, it then gets trapped or hardened into a solid carbon shell. Now, if you've ever toasted a marshmallow and you've accidentally lit that marshmallow on fire, when you do that, you've actually created carbon as well. It's very dark in color, just like we see down here on the table. And the reason we call these sugar snakes is that as those bubbles are formed, they form almost like long stringy tubes, which are kind of difficult to see from this camera angle. Maybe I should have had my document camera because they look much better on top. But there's a big difference now between our two reactions. Even though we started our powdered sugar reaction first, that reaction is now going much more slowly and calmly than our granulated sugar over here. The granulated sugar is now creating some pretty massive fire snakes or sugar snakes. They're continuing to grow out of that pile. And until they run out of fuel in the form of sugar, they are not going to stop creating this carbon dioxide gas, which is being then trapped inside that hardened carbon shell. Now, they sell sugar or fire snakes at fireworks stands. They are usually best done outside. I would highly recommend doing them on the dirt or in some sort of sand, because as you can see, our fire snakes don't have anywhere to spread. As our reaction goes to completion, the sand doesn't have any fuel in it. The sand is not flammable. It's also pretty heat resistant. And so our flame is not going to exit that small area where we had lit the lighter or the isopropyl alcohol. Now, we said that if we, of course, want to stop our reactions, right? Right now, they still have a lot of fuel to burn. There's still a whole lot of fuel down there underneath. Ooh, our one reaction is going pretty cool now. Let's see if we can take one last look before we try to extinguish them. But we said that the easiest way we will have in order to snuff our reactions is by smothering them. We can't really remove the fuel. One way we could smother them would be by dumping sand all over them. If you've ever heard of the phrase, you should never pour water on a grease fire, that phrase is 100% correct. By adding water to a grease fire, you can create a pretty massive fireball. So they sometimes will recommend that you sprinkle something like sand or baking soda over the flame in order to suffocate it to remove that oxygen. But the easiest way I know how is just to take a metal or fire-safe dish and place it over your reaction. Leave it there for a few seconds. Make sure that it is totally run out of oxygen. You can always do a double check. definitely out there, and again over here. Again, leave that there for a few seconds. Just make sure that that reaction consumes all of the oxygen down underneath that plate. And if you'd like to be extra safe, you can, of course, cover your sugar snakes with some sand, making once again sure that there is no more combustion happening on that plate. Now, we've got another really cool science experiment. This one is not necessarily a combustion reaction. We are not going to create any fire, but it is extremely exothermic. When we say exothermic, right, we mean that it produces heat. As this reaction goes to completion, we are making and breaking bonds, and somewhere in that process, there is energy left over at the end that's not being used for chemical bonds, and so it is released into the environment. And we can usually absorb this as, or feel this as heat. Combustion reactions are extremely exothermic, but they are not the only exothermic reactions. We've talked about another really popular exothermic reaction here on Echo Live. It's one that we call elephant toothpaste. I'm sure that you've all seen it online. It is really fun and exciting. Does anyone remember what the main ingredient of a elephant toothpaste reaction is? What is the main ingredient or the main chemical that we use? Give you a hint, it's probably something that you have at home in your medicine cabinet. It's probably something that you've used to put on your cuts or scrapes. Let's see. Let's see. Well, I'm looking at our chat to see if we had any questions about our first few reactions. But if you know the ingredient for elephant toothpaste, tell me that too. Leslie asked, are there any naturally occurring chemicals in nature that could possibly mix and combust? And that is entirely possible. Every chemical that we use here, right, comes from an element on our periodic table, which means that they are naturally occurring here on Earth. And so it is possible. It's not common. Otherwise, we might have spontaneous combustion happening all the time. But in most cases, the reason we call it spontaneous combustion is because it is incredibly rare. The conditions have to be exactly right. You have to have either some sort of heat source going into a combustion reaction usually, which usually can come from something pretty extreme in nature, like a lightning strike or something else like a downed power line, but doesn't really happen all the time. So it's not really something to worry about. Evan from Texas knows exactly what I'm talking about when we're talking about elephant toothpaste. He told me hydrogen peroxide. But it's not the hydrogen peroxide we have at home. So maybe I should have prefaced with that although we have hydrogen peroxide at home, we use it to clean our cuts and scrapes. This is not that stuff. It looks pretty similar. It's still a clear liquid, but the stuff I have in the lab is much, much stronger. The stuff that I have poured just into this small little water bottle here, this stuff is 30% hydrogen peroxide. The stuff you have at home is probably about 2 or 3% peroxide. And if you think about that stuff, right, when you put it on your cuts and scrapes, it burns really bad because this is an oxidizing agent, but that stuff is pretty weak. This stuff is about 10 times stronger, which is why I have on a different pair of gloves, not my fire safety gloves, because we said this is not necessarily a combustion reaction, but my gloves are here to protect me from a chemical burn. So just one more safety feature for our episode today. Now, for this one, we're talking about what we call a decomposition reaction. When we hear the word decomposition or decompose, what does that make you think of? Now, usually we think of things decomposing in nature, right? We've talked about decomposition when we talk about our compost bin, right? We threw things in our compost bin that we wanted to break down and turn back into soil or nutrients that can then go into our garden. We can think of living things decomposing as well as when things die and then become back part of the earth. But when we're talking about a decomposition reaction, not a combustion reaction like Evan told us, we are talking about something breaking down from being a very, very complex molecule into something a bit more simple. Yeah, so plants certainly decompose as well. And Nick, yes, this is food grade hydrogen peroxide. So this stuff is not safe to put on your skin. We do use it sometimes in food processing, but this stuff is not edible, not safe to get on your skin. It is extremely dangerous and highly, highly corrosive. So this is not the kind of stuff you could get at the drugstore. Now, when we talk about decomposition reactions, it might be helpful to have just one more image here. And this is just a diagram of a decomposition reaction. We said it is something, a complex molecule, like something like AB, turning into A and B, two very much smaller and more simple atoms or molecules. Now, the chemical formula for hydrogen peroxide is H2O2. It sounds a lot like water or H2O, but it just has that extra oxygen molecule attached to it, which makes it highly unstable. Hydrogen peroxide is highly unstable. It really wants to be water, so it's constantly in a state of breaking down, decomposing into H2O and oxygen gas. We know that when we use it for elephant toothpaste, we usually add all sorts of crazy things like food coloring and dish soap. And then the very last thing we add is the most important, because right now our decomposition reaction is happening. Our hydrogen peroxide that's sitting just here in the very bottom of this plastic bottle is going through a decomposition reaction. There is energy in the room all around us. Those molecules are bumping into each other, getting activated, breaking down, and turning into water and oxygen gas. It's just going incredibly slowly. So slowly that if we wanted to wait for this stuff to turn back in to water and oxygen gas, we would have to wait here for about 6 months. And I know I have some pretty exciting summer plans coming up. I'm sure you all do as well. And so we won't sit here for 6 months. We need to add something to this reaction instead that is going to act as a catalyst. A catalyst is something you add to a reaction that speeds it up, gives it the energy it needs to decompose or go to completion, but it's not actually involved. So no matter the catalyst we add to this reaction, it's still just breaking down into hydrogen peroxide and oxygen gas, but we need something that's going to make it just go a lot faster. Now, I'm pulling something out that we've already used today. This is, again, potassium permanganate, which is a heavy oxidizer. Oxidize, oxygen gas, right? This is going to rip apart those hydrogen peroxide molecules really, really quickly. It's going to turn them into rapidly decomposing water and oxygen gas, and we'll get to see that right here in this bottle. This one is pretty cool and exciting, and you'll notice that it only takes just a couple tiny little granules, almost less than a quarter teaspoon of our potassium permanganate here in order to get this reaction to go all the way to completion. So instead of taking 6 months, this is going to be the instantaneous decomposition of hydrogen peroxide. So here we go with our decomposition reaction in 3, 2, 1. Now, what do we see? What is this, you guys? Now, another safety thing we always do in the lab is I'm noticing something kind of funny. This has a certain smell to it. And so I'm wafting it. So I'm taking my hand and I'm carefully just pulling that substance towards my face. I'm not sticking my head right over the bottle and taking a big breath of it. What do you guys think that was? I guess you can't waft, so let me think about how this reaction smells while you tell me what you think that was. What did we create? If we said this was not a combustion reaction, it can't be smoke, right? So smoke is only a product of fire or a combustion reaction. And we said this certainly was not. So Evan tells me this is steam. You're exactly right. We said that this reaction is exothermic. It is incredibly hot. It actually got so hot that if you take a look at my bottle here, it shrunk to a little bit smaller than it was when we started that reaction. It kind of heated up the plastic, caused those molecules to contract as they cooled. And so our bottle looks kind of funny now. I'll tell you, from touching it, the bottle is really, really warm. And so what we were observing was that steam. This reaction got so hot that it actually caused the air molecules or water vapor to vaporize and turn into steam, just like you would get in the shower. Justin said, RIP to this cup, and you are exactly right. I'm actually just going to go ahead and seal that up, put it off to the side, but this reaction was one of my favorite. I have it set up so that we could do it one more time all together. But before we do that, I would, of course, love to pause and see if we have any questions before we go. If there are no questions, we do have a very exciting announcement today. Thank you to everyone who has filled out our Echo Live evaluation survey. It was so great to hear what you all think. I appreciate your ideas and your feedback. I've got so many new ideas for programs and episodes of Echo Live that I would like to do. If you didn't fill it out, you can still fill it out. But there was an opportunity by filling out that survey, if you had done it before last Friday, that you could enter to win a free week of our virtual summer camps, which start on Monday. Not today, Monday, but next Monday. We have been providing Echo Live to you for free every weekday since quarantine started, and we will continue these on a weekly basis throughout the summer. But of course, our summer camps are an exciting way for people to get an even more up close and engaging experience with science and to interact with me and some of our educators actually on camera and on a little bit more personal level. So everyone who filled out the survey and elected that they might be interested in winning a free week of camp was entered into the survey. We used a random number generator in order to pick a winner. And the winner of our free week of My Size Spark camps is Courtney Poloni and your second grader from Macomb, Michigan. Now, Courtney, we are going to follow up after this episode by sending you an email. We'll need some information from you about which week of virtual summer camp you might like to have with us. We are really excited to have you. If you did not win our free week of My Size Spark camp, registration is still open. You can still sign up. It is a great way, like we said, to do shows like this, to try experiments with us, to interact with us on a personal level. We are going to do some really cool things over the next 3 weeks. Now, we said we had this experiment set up one last time because I figure we might as well just go out with a bang here today. So a little bit more of our hydrogen peroxide down there inside our glass beaker. Tiny bit more of our catalyst, our potassium permanganate, because it really just doesn't take that much. And our last reaction of the day. Thank you all so much for joining in 3, 2, 1. Ta-da! Thank you, everybody. I hope we'll see you back here tomorrow for our last daily episode of Echo Live. Otherwise, we will continue seeing you all throughout the summer. Thank you all so much for joining.